Yeah, thank you very much for the introduction, and quite a lot of people here who want to know what crate not to use. So my name is Colin, and I have worked on Windows linked lists in safe and idiomatic Rust, and I have come up with a crate for that, and I will then tell you not to use it, or at least use it for the right reasons. So first, a little bit about myself. What led to this project is definitely my 15-year involvement with the ReactOS project. So for those who don't know ReactOS, it's basically open source Windows. So what we do is an operating system written from scratch, compatible from kernel mode up to user mode. So what we can do is not just use software written for Windows, but also the kernel mode drivers written for Windows in an open source operating system. And this distinguishes us from any other Windows-related project out there. And what also needs to be said today, ReactOS is not related in any way to the React JavaScript library. There have been too many people mixing the two projects up, so that needs to be said. I actually took the red pill in 2017, and it opened up the entirely new world of Rust to me. I had the unique opportunity to work on Hermit Core, which is a unikernel developed at my university's institute. It's a C project, and I had the opportunity to port it from C to Rust as part of my master's thesis. And within the 6 months of that project, it wasn't just possible to port the entire kernel, but the result was also better maintainable, easier to read, and it has superseded the C original in the meantime. Actually, the logo you see over here, the crustacean, has already been the logo right from the beginning. So you could say that project was more or less destined to be rewritten to Rust one day. So since that success, I've been trying to bring both of my passions together for Rust and for ReactOS. And this is what I've done with a big project. My idea is to write a ReactOS or Windows bootloader purely in Rust. You have to know the Windows boot process is much more complex than the Linux one. You need to parse the configuration, which is stored in the registry. You need to load a few files from disk, and the disk is usually using the NTFS file system. And in the end, you also need to pass a structure to the kernel, which is kind of complex. And for that project, I decided to build the individual parts as reusable building blocks via Rust crates, because it's so much better, especially when those crates are no STD compatible. So I've released NT-Hive, which is for parsing Windows, Hive, or registry files. I've released a low-level NTFS library this year, and I had a 1-hour-long talk about it at FOSDEM. So if you're interested in that, check it out. It reveals quite a bit of NTFS file system internals and how to implement them in safe Rust. And well, today we are here. I'm presenting NT-List, which is also a no STD library, and this time for Windows linked lists. So for someone presenting a linked list crate today, I'm making a bold statement: don't use linked lists. But what's actually wrong with them? So let's imagine this rectangle is our RAM. So now we create a linked list via a head pointer, and the first element gets allocated somewhere. The second element, as soon as we allocate it, is at a totally different place in memory. Same for the third, the fourth, and so on. This is quite a bit of memory that needs to be allocated just for storing 5 integers in this example. But on top of this, we also need to maintain a few pointers between all of these elements. So you see quite some chaos. I don't want my memory to look like this, and neither does your CPU. If we just add 5 elements to a vector instead, our memory more looks like this. So we have nicely 5 integers next to each other. We don't need any pointers between them. And knowing that they are next to each other, we can also jump to each element in constant time. We don't need to follow the links in linear time as we would need to do for linked lists. Your CPU will also like that, because as soon as you access the first element, it will already have adjacent element cached, so the next access to one of them is much faster. The caveat here is that a vector needs to allocate a new buffer every time that the old one is outgrown and you actually add more elements. But this downside generally outweighs the benefits. This benefit generally outweighs the downside, because you usually add elements first and then read much more often. However, there are a few good reasons when it makes sense to use linked lists, or when they are simply unavoidable. First of all, linked lists only allocate elements once in their lifetime. So this is pretty useful in situations where you don't have an overview about all the callers that currently hold references to the elements. So especially for pre-Rust code, where such reference handling is impossible, and you want to make sure every caller that had a reference once shall still have a valid reference as long as that element is part of the list. Wouldn't be the case if the vector gets reallocated in between. Secondly, for the vector, you can only push to the end. There's a vecdeck in Rust, which is a double-ended queue, where you can push to the front and to the end. But linked list can also insert elements in the middle, at least if there's an API provided to that. Not all linked list implementations have that, but theoretically it's possible without shifting elements around. And finally, due to all the above reasons, linked lists are widely used in existing kernels, and this is basically why we are here today. So no matter what good reasons we have for using a vector, if there's an existing kernel that is using a linked list and we want to be compatible to that, then we also need to support linked lists, just to maintain compatibility. Now, a lot has been written in books about linked lists, and the textbook example usually goes like this. So you have the two previous and next pointers, and you have a data element of some arbitrary type. Let's say we want to manage device drivers with their names and file paths via a linked list, and we make up a driver structure. So this could look like this. In contrast to that, a Windows linked list is a so-called intrusive container. What that means, let me show you. We first remove the data field again from that structure, so only the next and previous pointers remain. The resulting structure is now called list entry. It has no type information whatsoever. And now if we create the intrusive version of our example driver structure, we just include the list entry element as a field. So it looks like this. That's it. That's the entire magic behind intrusive containers. The conceptual difference is that more and more responsibility shifts from the linked list to the implementation, to the caller. So the caller has to add the entry field to its element structure, and the caller also allocates the memory for the entire element structure and needs to guarantee that this is valid for the entire lifetime of the list. Usually that's not what we like in Rust, if the caller manages memory instead of when Rust or a Rust crate manages memory. Anyway, this is the reality. This is what also a Windows linked list looks like. So trigger warning, I have to show some C code from time to time here, but I made sure that it's all indicated in this nice blue screen color. So what you have here is basically the Microsoft implementation of a list entry. It looks just like what I've just shown, except that the next and previous pointers are called flink and blink, meaning forward link and back link. And this implementation actually comes with a few APIs. So there's one initialize list head to actually initialize it. I will tell you soon what initializing means here. We have insert head list, insert tail list to insert elements at the front and the back. Notably, there's no API for the Windows linked list to insert an element in the middle. We have 3 APIs to remove entries, again, front or back, or if you already have a pointer to that element that you want to remove. And finally, there's containing record, which is actually a macro, but it returns a pointer. And what you can do is, if you just have the address of the entry field, you can get the address of the entire element structure and vice versa. This is a calculation that containing record performs. So a basic example can look like this. This is entirely taken from a Microsoft sample driver, so it just manages notification events. And a more complex example, which I show here, is directly taken from the ReactOS PE image loader. What you see here is another property of Windows linked lists. A single element can actually be part of more than one list at the same time. So you have 3 list entry fields here, just for the same element in different lists. And that also means list entry is not necessarily the first field of the structure. Finally, I had a look through the ReactOS code base. When you just look for list entry, you currently get 644 results. So you really see that structure is ubiquitous in the Windows kernel world. And if we want to program it in Rust, then we really need some good support for that. So how do we build a safe Rust interface around it? Before we actually move to that, it's important to highlight another detail of Windows linked lists. If we look at the textbook linked list example again, we have head and tail pointers pointing to the first and the last elements, and both elements are interconnected via their next and previous pointers. When there are no previous or next pointers, these fields are filled with null pointers. Keep that detail in mind. When we look at Windows linked lists, the interconnections between the elements are the same. The head is a list entry structure itself, so it replaces the head and tail pointers we just saw, but it's basically the same. But what makes this linked list distinctive from the textbook example are the back references to the head. So you see, whenever we are at the first or the last element, there are no null pointers, but the entry is linked back to the head. Let's give that some time to sink in, because it has a few implications. First, we have to be very careful when iterating through the list, because most implementations for that check for null eventually. Here, you have to check for the head address. What's even more important, if we see that in a Rust context, the head address now also needs to be stable. Rust likes to move memory around, but here we actually have to make sure that the address of the head element doesn't change in its lifetime. So you see, with all these constraints, there have been various challenges I had to overcome to create a safe Rust implementation, and Rust has been very helpful here, so thank you, Ferris. The first challenge is fairly simple. So list entry describes a doubly linked list, and all Rust guides basically tell you that doubly linked lists are not good because two mutable references to the same memory are prevented by the borrow checker. So what we simply have to do is use unsafe here. This is also what the Rust collections linked list library does internally. We basically only have to move to mutable pointers, but otherwise this is pretty doable. So not that much of a challenge. Coming to the next challenge, this is more of a problem for an idiomatic Rust implementation. So as we've seen, the original list entry has, the list entry structure is used for both the list head and the list entry. What we rather want is a distinction here. So there should be a list head which provides some nice methods like all the std collection containers. And you want a simple list entry structure which you can embed into your element structure. So what I'm doing here is artificially splitting up the original list entry into anti-list head, which provides my methods, and anti-list entry, which I embed into my element structure. We can freely do that if we just keep the memory layout the same. So this is less of a hack than it might look. What we also now need to consider is we need a stable address to the list head so that we can reference back to the list whenever necessary. And this is actually possible via pinning. Pinning wasn't always part of Rust. It has been introduced as part of the async await move. And this, for the first time, makes stable back referencing possible. So now, when we create a new empty list, Flink and Blink already need to point back to the head address. But how can I do that? This is what initialize list head actually does in C, and why I need to call initialize list head when I start, because otherwise the lists can't be seen as empty. I want to make it impossible to misuse my crate, so nobody should be forced to call some init function. It should be initialized right when I return the list head from new. But I can't self-reference myself from new because I don't know the final address yet. And as soon as I return the self structure, it gets automatically moved. So what can I actually put here for Flink and Blink to self-reference? I have found the move-it crate to be tremendously helpful here. What we now do is first create a Flink and Blink with potentially uninitialized memory. And then, thanks to the features of the move-it crate, we can add another closure, which actually gets the final address after self has been moved and got its final address. And this is what I put into Flink and Blink now. And thanks to macro magic, that closure, which I specify with the with function, is actually called all the time when I call new and get my initial list head structure returned. So this way, thanks to the move-it crate, I can get a list head that is initialized right from the start. So another challenge solved. Let's get to the third challenge. Our list entry right now lacks any kind of type safety. To see what I mean by that, let's imagine what our driver list example from the previous slides would look like in C. So we have some driver list head somewhere, and we have the driver structure, and what you already see here is the list head and the entry field both share the same list entry structure. So if I now call the insert list head function, it accepts two parameters of type list entry. I could already mix them up, no type safety at all in the C original. But to make it even worse, I can push any kind of structure into the same list head. So here I have a process structure, and nobody would actually stop me from pushing processes on a list that was meant for drivers. We don't want that. The Rust implementation shall actually make that impossible. And this is again where Rust's type system can help us tremendously. What I do when I now translate list entry to a Rust structure, this is the original, I can just add a type parameter e with a newly introduced anti-list element trait, which I now need to implement to all of my element structures. And when I then push that, my pushback function will only accept elements of type E. So this is already a first step on making it type safe. Is that enough though? Spoiler alert, it's not. Recall again, an element structure may be part of more than one list and therefore contain more than one link. So our driver example in C could also look like this. It's not just enough to distinguish by list element type. We also need to make sure that pushing to drivers by name list head will only affect links sorted by name, and pushing to drivers by path list head will only deal with links sorted by path. So what I do, coming back to my Rust implementation, is adding a second type parameter L for every list based on a new marker trait, anti-type list. So let's introduce that marker enum type for the drivers by name list. We implement anti-type list on drivers by name list. And now we can use it as a type parameter. We can do the same with drivers by path list. And this actually gives us distinctive types. So nobody can accidentally push to links sorted by name when they actually wanted to push to links sorted by path. Our challenges don't end here though. As we just saw, entry fields can also have arbitrary names and positions inside the structure. So how do we get the right field? As we just saw, we have anti-list element, and what I now do is I add the L parameter to anti-list element as well, which allows me to implement anti-list element for all lists and also an offset method for every field inside the element list. What that means is, for the driver example with 2 links, I have one implementation of offset for links sorted by name. I have another one for links sorted by path. And the offset method just returns the actual field offset with 2 8-byte pointers. That means the first field is actually at offset 0 and the second one is at offset 16. Finally, the hardest challenge of all, how do we handle memory when a single element can be part of more than one list? To my knowledge, this is not doable in Rust, in safe Rust, while staying compatible to the C original. I mean, 2 lists owning the same element simultaneously would violate the basic Rust memory ownership model. A reference counter could help here, but we can't add that without violating compatibility to the C original. So what I did instead was providing an unsafe base implementation, which relies entirely on the caller to manage memory. But for the happy path, for the common case that an element is only part of a single list and the element is allocated on the heap, I can actually provide a safe implementation, and this should work for like 99% of the cases. So now we have the common path split from the bad one, and we don't need unsafe that often. But at least we have an option to deal with all Windows linked list scenarios in Rust. Let's come to the results. Was it worth all the hassles? So I promised macro magic a few times, and what we have here is, if you lost track of all the traits I introduced, let me show you, we have derived macros for them. So I don't need to implement NT-list myself on drivers by name list or drivers by path list. Thanks to macro magic, I can just derive them. And even more important, I don't ask you to implement the offset method yourself. What I simply provide is a macro to derive NT-list element for the entire driver structure. And that proc macro is actually a bit more complex. It will look into the entire element structure for NT-list entry fields and then implement NT-list element for all of them with the correct offset. Finally, there's also the boxed attribute, which you can use to designate the single link that shall be used for the safe implementation. So basically the link that owns the memory for this driver element. So let's now look at some C code and the equivalent in Rust. So C code again, I'm sorry. For that, let's imagine a process list that employs the process structure I just presented. And we just want to calculate the total memory usage of all processes. In C, this currently amounts to this code, just for calculating a total sum. And there's a lot that can go wrong here. So first of all, we have to get the exit condition right. We have to check for the address of the head element, not for null. And we also have to get the parameters to the containing record macro right. There you can basically, as this is a macro that is not checked, you can basically put any kind of parameters into them. And you can also get quite some different output out of it, but you still have to fetch the process element on every iteration yourself. There is nothing nicer that C actually provides. And only then I can finally get to do what I wanted to do in the first place and sum up the total memory usage. If we translate that to Rust using the NT-list crate, it's as easy as that. We can just fetch an iterator and sum up the memory usage. But as this is an iterator implementing the iterator trait, it can do even more for us. We can actually turn all of this into a single statement and use the sum method to get the same result. So this is really as easy as it can get to achieve the same that the original complex C code did. Now let's look at removing elements, which is even more complex in the C original. So I already had to remove the one condition from the for loop because the next pointer or the flink pointer may not be valid anymore as soon as I have removed it from memory. So a lot that can go wrong here again. I need to save the next pointer before removing it. I need to pass the right pointer to remove entry list, which is current, which is the field. And then I need to pass another one to the actual memory freeing function, which is process, which contains the current field, but still it's a different pointer. I have to get all of this right, and there's just so much more that can go wrong here in the C original. So there is no value in debugging all these issues over and over again. So it's great if such common patterns are handled better. And in Rust, well, this would amount to this single line if we just use the retain method. I have found Rust to be really good at identifying such common patterns and providing building blocks for them. So I actually got retain from the vector collection, and it basically is usable for the common case that you want to iterate over all elements and check for a criteria and only keep some elements based on that criteria and remove the remaining ones. So coming back to the original question, was it worth all the hassles? I think that's a clear yes. I have just seen so much C code where things were handled wrongly, and I really want to see these issues becoming no-brainers in the future with a Rust implementation that supports linked lists. Finally, my original idea was to make it compatible to the C original, and I wanted to prove that as well. So what you see here is the Windows debugger, quite an old version of the Windows debugger. It definitely doesn't know about Rust. What it knows about is the PDB debug symbol format emitted by the Rust compiler for Windows, so it can even debug Windows Rust programs. And what it can also do is it has the -list command, and if you step into the binary while debugging it, you can actually traverse and dump all the contents of a linked list thanks to that macro. And this is basically what I'm doing and what I'm proving here. I have set up a simply linked list that just pushes some integers, and I stop right in the middle, use the -list command, and it shows me the same linked list with the same values. So that was like the final proof required that my implementation is fully compatible to the C original. And with that, I'd like to conclude my presentation. Thank you very much for listening. All what I've just presented is on GitHub and crates.io if you like to check. But don't forget, if you can avoid a linked list, if you can use a vector, continue doing that. But if you need to use a linked list for whatever reason, be it on Windows or maybe Linux also has a compatible one, then you now have a tool to make it possible in a safe and idiomatic Rust way. Thank you very much for your attention.